This video is about enthalpy and stoichiometry and drawing a reaction diagram, saying whether something's exothermic or endothermic. Alright, so for this first reaction here, you have 4 moles of iron reacting with 3 moles of oxygen, producing 2 moles of iron 3 oxide. And I tell you that delta H for the whole reaction is negative 1,625 kilojoules. So before we even get started, I want to think about that a little bit. Whenever you do delta H, or really delta anything, it's always final minus initial. So for us, the final thing are going to be the products. The initial is what we start off with, and that are the reactants. So when you do delta H, and H is enthalpy, it's just basically the heat content of the system. You're going to do the enthalpy of the products minus the enthalpy of the reactants. And if you end up with a negative number, what that is telling you is that the reactants have a higher enthalpy than the products. So then what you're doing is basically a small number here, subtracting out a large number, and that's why you get a negative number. So what it's telling you is the chemicals are basically releasing heat to the surroundings, because remember, you have the chemicals point of view and the surroundings point of view. Delta H is always from the point of view of the chemicals. So the chemicals are losing heat, and you know that's because it's negative. So if the chemicals are releasing the heat, they're losing the heat is going to the surroundings. All right, now this first question here, it says how much heat will be absorbed or released when 16.50 grams of iron reacts. This is going to be like a stoichiometry problem. Always write down what I give you first, 16.50 grams of iron. And whatever units you start off with, they end up on the bottom in the next step. So since you start off with grams of iron, we're going to put grams of iron on the bottom. And what we are doing is a mole conversion, just like we did in stoichiometry, converting between grams of iron to moles of iron. The grams we get from the periodic table. 55.8 grams of iron is 1 mole. Right? That is the conversion factor. The next step, it's kind of like a modified mole ratio is how I think about it. What happens here is the grams of iron cancel out. And what we're left with is moles of iron on the top. So we put that on the bottom in the next step so they'll cancel out. And what I want to know is how much heat is released according to that equation for the number of moles of iron given in the equation. And since I say 4 moles of iron here, I'm going to put a 4 down there. For every 4 moles of iron consumed, the reaction releases 1,625 kilojoules. When you go up to the equation to get the heat term, you also use the coefficient of whatever substance you are looking at, because this is for every 4 moles, it's negative 1,625 kilojoules. So I'm going to write mole ratio here. It's kind of like a mole ratio. Moles of iron will cancel out, and now you do the math same way as always. 16.50 divided by 55.8 multiplied by the heat term, which is negative 1,625 kilojoules, divided by the 4 moles, rounded off to match the number of significant digits given in the problem, which is 4. It gives you negative 120.1 kilojoules. Now the question asked, will it be absorbed or released? So I would just want to make a note of that. I'm just going to say 120.1 kilojoules released. I took the negative out of it just because using the word released is really saying the same thing as having a negative delta H. The chemicals released that much heat. So is this reaction exothermic or endothermic? I keep saying released. When the reaction releases heat, it is exothermic. So I don't have this question on here, but a good question is, how would we measure this in terms of temperature? Would temperature increase or decrease if we had a thermometer in that reaction, basically? What would happen? And since the chemicals release the heat, they release it to the surroundings. And what we measure are the surroundings. So temperature would increase at that point. Remember, whatever the chemicals, the system itself does, in terms of heat, the surroundings do the complete opposite. In this case, the system, the chemicals, release the heat, so the surroundings absorb the heat. And remember, we measure the surroundings, so we would measure that as a temperature increase because the chemicals released heat. So, same thing as what letter C is saying. Heat was released or absorbed by the chemicals. Released. Rewrite the original equation as a thermochemical equation, N for 2 moles of iron. The equation, the original equation up here, I have it in what's referred to as delta H notation. The heat term is not written as a reactant or a product. Delta H is written off to the side, and I put a negative sign with it. So now when I ask for thermochemical, you basically take that heat term and you write it as either a reactant or a product. You have to pay attention to which side it should go on. I keep saying heat is released in this reaction. It's generated. Just like you generate iron 3 oxide, you're also generating heat, so it goes on the product side. Now the other thing we have to pay attention to is it says 2 moles of iron, but the original equation was for 4, so we have to take that into account. So now I rewrite everything for 2 moles of iron. So since iron was divided by 2, everything else must be divided by 2. So you get 3/2 of a mole of O2. If you want to write it as 1.5, that's fine. It's really saying the same thing. 2 moles of iron 3 oxide become 1 mole of iron 3 oxide. And now we have to put the heat term in. And I've been saying heat gets released, just like Fe2O3 gets produced. Well, the heat gets produced. But I also have to divide that by 2. So 1,625 kilojoules becomes 812.5 kilojoules. Remember, heat is extensive. If you change the amount of the substances, the chemicals, you are going to change the amount of heat either absorbed or released. The other thing you want to pay attention to is I did not write a negative sign here. Even though delta H is given as negative, you don't put a negative sign when you write the thermochemical equation. What happens is it being on the product side is basically saying the same thing that having a negative delta H tells you, that heat is released and that it is exothermic. All right, so that's how we do those types of problems. Now we're going to have to draw a reaction diagram, so I have to erase this and scroll up. But just keep in mind what I said up here. For you to have a negative delta H, the reactants have to have higher enthalpy than the products. All right, so that's telling us that the chemicals themselves release that heat energy. All right, so let me scroll up here. All right, it tells us to label a bunch of stuff, so let's get an X and Y axis on there. Progress of the reaction, I'll just write that as reaction progress. It's a little easier to write. Enthalpy goes on the Y axis. Sometimes you might see that as potential energy. It's really just talking about the heat content of the system. Now, since this is exothermic, we said the enthalpy of the reactants is higher than the enthalpy of the product. So you put the reactants nice and high. I'm going to rewrite it for the original equation. So it's 4 moles of iron and 3 moles of O2. And they release heat, so the products end up lower. The product was 2 moles of iron 3 oxide. So right now we have progress of the reaction, we have enthalpy, we have the reactants and products labeled. The only thing left is delta H, and that's what was given in that original equation, that negative 1,625 kilojoules. So now this hopefully all makes sense. The reason why you have a negative delta H, because remember, delta H is from the point of the view of the chemicals. Whenever you do delta, you do final, which are the products, minus the initial. So you're doing something that's low on the y-axis, so a relatively small number, minus a relatively large number is going to give you that negative delta H. And if the chemical is released about 1,600 kilojoules of energy, the surroundings absorbed about 1,600 kilojoules of energy, which is why we see that as a temperature increase. All right, I'm going to go on to another example. All right, this one looks a little different. Delta H is positive. And I have 6 moles of carbon dioxide reacts with 6 moles of water to produce 1 mole of C6H12O6 and 6 moles of O2. So this should look kind of familiar if you took bio. What happens here is how many grams of C6H12O6 can be produced when 81,740 kilojoules of solar energy is supplied in the reaction for photosynthesis. All right, start off with what I give you, 81,740. Let me write that the right way. All right, now I start off with kilojoules. So I have to put kilojoules on the bottom. And this is like that modified mole ratio step. The kilojoules I get from the equation. It's 2,803. I'm looking for C6H12O6. So since I came up to the equation to get the heat term, I have to use the coefficient from the equation as the number of moles, because for every mole of C6H12O6 that gets created, that involves 2,803 kilojoules. So now kilojoules cancels out. What you're left with is moles of C6H12O6. We want to get 2 grams. This step is like the conversion factor. It's always however many grams off the periodic table is 1 mole. So to save some time, from the periodic table, that all adds up to 180.0. So when you do the math for this, 81,740 divided by 2,803 multiplied by 180, rounded off to the right number of significant digits, that gives you 5,249 grams of C6H12O6. Now is it exo or endothermic? This one ends up being endothermic. The delta H being positive tells you that the products have a higher enthalpy than the reactants, because remember when you do delta H, it's final minus initial. So it's products minus reactants. A positive number means you have a higher number for the products than the reactants. Now, what does that mean in terms of temperature? Well, the chemicals went up by 2,803 kilojoules, because remember delta H is from the point of view of the chemicals. So the surroundings went down by 2,803 kilojoules, so the temperature in this case decreases, because remember we measured the surroundings. Heat was absorbed by the chemicals because delta H is from the point of view of the chemicals, and that number went up. Rewrite the original equation as a thermochemical equation, and for 2 moles of C6H12O6, well, it starts off with 1, so I have to double everything. 12 moles of carbon dioxide, 12 moles of H2O. Now I have to write it as thermochemical, so I have to include the heat term. And since it's endothermic, the heat is absorbed by the chemicals. They act as a reactant. I doubled it because you start off with 2803, and if I'm doubling everything else, I have to double the heat term because heat is extensive. It depends on how much material you have in there. That gives me 2 moles of C6H12O6 and 12 moles of O2 because I'm doubling everything. So now we have to draw the reaction diagram. And since this is endothermic, and I was saying it being a positive delta H, that tells me that the reactants start out low and they will end up increasing. So let me get the labels on here. Reaction progress on the x-axis, enthalpy on the y. I'll rewrite it for the original equation. You have 6 moles of carbon dioxide plus 6 moles of H2O. Goes to 1 mole of C6H12O6 and 6 moles of oxygen. Delta H ends up being a positive number, and we gave it as 2,803 kilojoules. You don't actually have to write a positive here. I'm just doing it just to emphasize the point. So it's positive because the reactants started out with low enthalpy. They sucked heat away from the surroundings. You can think about it that way. Basically, heat was supplied to the system. The chemicals are now storing that extra heat energy in the bonds of the products. So delta H is positive. And that's why we see it as a temperature decrease, because the chemicals absorb the energy.